So in general, we can say we know the definition of a limit, right? Well, is x approaches a of f of x. Well, a lot of times we can just calculate that limit by plugging it in. But what has to happen for that to work, the function has to be continuous there. You know, if you had if I had a piecewise function and maybe I graphed it and it looked like this, could I just plug x equals 1 into my piecewise function and get that correct value? No. And the reason is because my graph is not continuous at 1. There's a break in my graph. Now, if it was just a solid line, could you plug in your 1 and get your value? Absolutely, because it's continuous. So when we can just plug in actually depends on if the function is continuous or not. So this is the big thing for today. There are 3 requirements to say something is continuous. First of all, f of a has to be defined. Okay? The function has to exist. Second, the limit has to exist. And third, those 2 things have to be equal. So the function exists, the limit exists, and they're equal at that point. Those are the 3 requirements for continuity. So today we're going to really just focus on looking at things and deciding if they're continuous or not. And if they're not, you're going to have to tell me which rule did it break. We know, this is kind of what we already said, it's continuous if there's no break in it. If it has a break, that point where you had the break is called the discontinuity. So I might say, is it continuous? I might say, tell me the discontinuity. And you're just telling me the point where it's not continuous. So we're going to start just by looking at a graph and identifying the discontinuities there. So here's our first example. I want the x values of my discontinuities. So where do I have the first one? Alex? At 1. X equals 1 is a discontinuity. When I say y, you're telling me which of the 3 rules did it break? Does the function exist there? No. Can you do f of 1? Is there a circle anywhere on this graph? No. So at x equals 1, it's because f of 1 does not exist. It broke the first rule. Okay, where else is it discontinuous? Do we have a discontinuity? At 3. Okay, let's see which of our 3 rules is broken. Does the function exist at 3? Yeah, I have a closed circle at 3. Does the limit exist at 3? No, because as you come in from the left and the right, they don't match up. So the limit as x approaches 3 of my function does not exist. Or you could just say the limit does not exist. I'm not looking for anything too precise. Okay, where else do we have a discontinuity? At 5. Does the function exist at 5? Yeah, when I go to x equals 5, I do have a closed circle on my graph, so the function exists. Second rule, does the limit exist? As I'm coming in from the left and the right, do they match up? Yes, so the limit exists. Third rule, are those things equal? No. F of 5 is up here, the limit is down here. So the limit doesn't equal the function. So that illustrates the 3 properties and the 3 ways we can have a discontinuity. Questions so far? at this graph. Right. If I want to graph this, we could, what are my options for getting a graph here? Make a table, plug in some points. If you put in a 0, you get -1/2. If you put in a 1, you get -1. Can you put in a 2? No. If you put in -1, you get -1/3. So this piece has a curve. If I put in a 3, you get 1. If I put in a 4, you get a 1/2. This is just a function with the vertical asymptote. If you remember 1 over x, this just moves it to the right too. You could use a graphing calculator too for homework and everything. So, where is this discontinuous? At x equals 2. Why? The limit doesn't exist and the function doesn't exist. It really kind of broke all the rules. So in this one, you could tell me either rule. You just have to give me one reason why it doesn't work. So you could say the limit does not exist. You could say f of 2 does not exist. Either one. Okay, let's look at another one. This is a piecewise. We know to graph piecewise, we do each piece separately. Essentially just a T-chart for each piece. The first one, you have to start at 0 and you want things greater than that. What are you getting out every time? 1. It's just a horizontal line. The second one, we have to put in 0. What kind of circle will that be? Then we need things less than 0. But what am I getting out every time? Okay. So where is this discontinuous? At x equals 0. Okay, why? Does the function exist at 0? Yes. Does the limit exist at 0? No. The left and right hand sides don't match up, so the limit doesn't exist there. So far, so good? I'm just going to keep looking at these. So, for example 2, let's go A. Can you tell me, without drawing a graph, could you just look at this and tell me where it's discontinuous? Where? 2. Why? Yeah. Can you plug a 2 into this? It's undefined. So you might, if it's a fraction, all you're really looking at is what makes it undefined, what makes the bottom 0. So this one is discontinuous at x equals 2. And what would my reason be? We said it's undefined there, so f of 2 does not exist. look at that one. 1 over x squared. That was one of those graphs we looked at in college algebra, and it looked like this. So it's 1 over x squared if x does not equal 0, and it's 1 if x does equal 0. So we had a fraction, which means I can't plug in a 0 there, but it's a piecewise, and I made a separate piece where you could plug in 0. When you're looking at piecewise functions, what has to be true for it to be continuous is those pieces have to match up. They have to touch one another. Is this continuous? No. So this one is discontinuous at x equals 0. Okay, my reasoning. Does the function exist at 0? Yes, I have a closed circle. Does the limit exist at 0? Both sides are going up forever. What is the limit at 0? Infinity. So there is a limit. Are they equal? No. So my reason, you can tell me, the limit as x approaches 0 of f of x does not equal f of 0. You can just say the limit doesn't equal the function. Either one is fine. I think I gave you guys a blank slide after this, so you had a little more space to work. C. I took that same function from part A, but this time I also made it a piecewise. So does it exist at 2 now? Yeah. Okay, let's talk about the graph here. If you were trying to evaluate the limit as x approached 2 right here, like we did on our last quiz, what would you do with that? Factor. So that would break into x minus 2 times x plus 1 over x minus 2. And what happens? The x minus 2's cancel and you get x plus 1. What that means, if you looked at your graph on the calculator, so it's just a line, y-intercept of 1, slope of 1. And it would have originally had an open circle when x was 2, because you couldn't plug a 2 in there. Remember we did holes back in college algebra? And we talked about when things cancel, that put an open circle on our graph. So this simplified into just a line. When x was 2, because you couldn't put it in the original, we have an open circle. And then it tells me it's 1 if x equals 2. So it has the point 2, 1. So does the function exist at 2? Does the limit exist at 2? Are they equal? No. So it's still discontinuous at 2. And our reason is the limit doesn't equal the function there. D. What's this? Greatest integer. What does the greatest integer look like? It's a step function. Remember, you can't get out anything bigger than what you put in. So if you put out anything between 0 and 1, you get out 0. Put in anything between 1 and 2, you get out 1. Between 2 and 3, you get out 2. And it keeps going. So we've seen that plenty of times. Is that one continuous? No. Where is it discontinuous at? It's at every single integer. There's a break at -1, 0, 1, 2, 3. Discontinuous at all the integers. Okay, why? Does the function exist at the integers? Yes, we have a closed circle. Does the limit exist at the integers? So at 0, does the limit exist at 0? No, because the left and right hands don't match up. So the reason would be the limit does not exist. Questions so far? So there are different types of discontinuity. In A and C, we saw what's called a removable discontinuity. So A and C, remember, were both the fraction, where that x minus 2 canceled out. A removable discontinuity is one where we could fix it. It's one where you have just an open circle on your graph, and we could fix it by just filling in that open circle. In part B, we had an infinite discontinuity. My graph was going to infinity. So if you have limits going to positive or negative infinity, so that's when you have vertical asymptotes, that's your infinite discontinuity. And in part D, that was a jump discontinuity because you physically jump from one piece to another. So a lot of times that happens with piecewise functions. If your two pieces don't match up, you have to jump from one to another. That's a jump discontinuity. We have been looking at overall continuity. You can also be continuous from just the left or the right. You know, if we wanted to look at it one-sided. To be continuous on an entire interval, you have to be continuous everywhere in the interval. So I just want to spend the rest of the time practicing continuities. And we're going to see if maybe we can get to the point where we can just look at the equation itself and decide. We want to know where this is continuous. So what we've seen so far, things where we have issues with continuity, what kinds of equations give us problems? If it's a fraction, then we can have discontinuities. And what was the other type?
Piecewise.
Piecewise. When you have those multiple pieces, we can have discontinuities. Okay, if I'm just looking at this, it's a polynomial. What do you know about the graph of a polynomial? Just a nice smooth curve. So I don't have any fractions, I don't have any piecewise issues. Is there going to be anywhere where I have a break in that graph? No. So where is it continuous? Polynomials are always continuous. If I want to know where this one is continuous, to answer where it's continuous, it's easier to say where is it not. Where would this not be continuous? Okay.
X equals -1/2.
Okay, so you just figured out when the bottom was 0. So it's not continuous if this denominator equals 0. So if you add your 3x, we actually get a positive 5/3 or 1 2/3. So it's not continuous there, so that means it is continuous everywhere else from negative infinity to 5/3, and from 5/3 to infinity. If I asked you why it wasn't continuous at 5/3, what would your reasoning be? The function doesn't exist. Okay. Another fraction, x cubed over x squared plus 2x plus 5. So we know it's not continuous when the bottom is 0. Does that factor nicely? No. What can we do if it doesn't factor nicely? Quadratic formula. Opposite of b would be a -2 plus or minus the square root of b squared minus 4ac all over 2a. Under my radical, I get 4 minus 20, which is -16. What's that telling me? It's an I. Do I even need to finish this right now? No, because in terms of my graph, are we graphing I's? No, this is imaginary. So, that tells me for any number I'm going to plug in, I'm going to get an answer. So where's this continuous? What do you think? We are trying to find where it's not continuous. You guys can talk out loud. You all just whisper. Make me read Blitz. The only place where it's not continuous is imaginary. So that means it is continuous everywhere. So it's negative infinity to positive infinity. Just because you have a fraction doesn't mean it will be discontinuous somewhere. It's possible that the denominator isn't 0. Okay. You guys do C. Decide where that's going to be continuous. What'd you do, Landon? Where the bottom is 0. Okay, so where is x squared minus 4 equal to 0? Oops. So if you add your square root, that means plus and minus 2. That's where it's discontinuous. So it's continuous everywhere except positive 2 and negative 2. So that means it's continuous from negative infinity to negative 2, between negative 2 and positive 2, and when you are bigger than 2. Everywhere except those two values. Okay, a few more. Now I'm asking you to tell me where it's not continuous and to decide if it's removable. So removable in terms of a fraction will be if something cancels on top and bottom. That puts a hole in our graph and that makes it a removable discontinuity. So if we factor multiply to positive 2 and add to negative 3, so my x minus 2's cancel, I get 1 over x minus 1. So that canceled. We have two places where this function is discontinuous. The first one is when x is 2, and the second one is when x is 1. Since the 2 canceled out, that is a removable discontinuity. Okay, if I asked you how to fix it, I didn't, but I could. You would just have to make f of 2 equal, we have to fill in the hole in our graph. If you remember in college algebra, when we found the holes, we figured out, okay, x minus 2 equals 0, that gave me the 2. If you plug a 2 into what's left, you get 1 over 1, which is 1. So if we filled in the bubble at 2, 1, it would solve the problem. It would be fixable. So that's removable. X equals 1 is not removable because it didn't cancel. What's going to happen at 1 on your graph? Where we're going to see a vertical asymptote, right? When you have vertical asymptotes, that's when you're going to positive or negative infinity. So what type of discontinuity would this one be? Infinite. So in these fractions, if it cancels, that's removable. If it stays on the bottom, it's going to be an infinite discontinuity. Okay, anytime we have something with an absolute value, what do I make you do? Do a piecewise, don't you? We have to rewrite it without the absolute values. That's going to be our theme throughout calculus. Anything we have to do, we have to get rid of that absolute value first. My 2 cases are based off what makes this 0. What makes x minus 1 equal 0? And that's just that x equals 1. So we'll have to worry about when x is bigger than 1 and when x is smaller than 1. If x is bigger than 1, does that absolute value have any bearing on things? No. So it would just be x minus 1 for x minus 1 cubed. What happens there? You can cancel one of them. So that's true if x is greater than 1. Can I say greater than or equal to 1? Can you plug a 1 into that? No, it gives you 0 on the bottom. Okay, so our case if x is less than 1. If x is smaller than 1, then what's in this absolute value would be negative. So it would do the opposite of it. You can still cancel one of them. You get negative 1 over x minus 1 squared. Okay. But I still have the issue. What number shows up? It's going to make both of these undefined. 1. So I have a discontinuity at x equals 1. It's from the bottom and it didn't cancel out entirely, so what kind of discontinuity would that make it? Infinite. If it stays on the bottom, you're going to have a vertical asymptote there, so it will be an infinite. We would say removable. We did cancel an x minus 1. If when we canceled it, we didn't have any more on the bottom, then it would have been removable. But because I still had it on the bottom, it's infinite. We're still getting a vertical asymptote there. And you can always look at a graph to kind of confirm that. Okay, let me ask you this question. I want to find a value that makes this function continuous. If a piecewise function is continuous, the 2 pieces have to match up at their breaking point. Okay, so if I just gave you any piecewise function and said, is it continuous? If I said, like f of x equals asked you if this was continuous, all you really have to do is look at the breaking point. What's my breaking point? 2. Plug a 2 into each piece. If I put a 2 in the first piece, I get 1. If I put a 2 in the second piece, I get 1. So that means my 2 pieces line up, so is it continuous? Yes. If my breaking point were -2, I put a -2 in the first one, I get -3. In the second one, I get -7. Then is it continuous? No. So for a piecewise, you just have to look at those pieces. I want to make this continuous. My breaking point is 1. So that means when x equals 1, I need these things to equal one another. So if I plug in my 1, 1 squared is 1, minus 2 is -1. A times 1 is A minus 4. Add over my 4. And A would have to be 3 to make that continuous. Is that one okay? One last thing I want to talk about today is the intermediate value theorem. This isn't new. You saw it in Algebra 2. We saw it in college algebra as well. The intermediate value theorem only applies if your function is continuous. That's kind of the piece that we glossed over in Algebra 2 and college algebra. But now that we have a good definition of what it means to be continuous, if you're going to use this, you have to state that it's continuous. And so all it tells us is that if you have a function and for one x value you get a positive number and one x value you get a negative. As long as this is continuous, what does it have to hit somewhere in between? 0. So if the function's continuous and you go from a negative to a positive or vice versa, somewhere in between those x's it had to equal 0. That's all the intermediate value theorem tells us. So we'll do a couple examples of that and then we are done. So example 7 says, show there is a root of this equation. Okay, that's a pretty vague one. A lot of times with the intermediate value theorem, I'm going to say there's an interval. I may say, show there's a root between 1 and 5. And you'll plug in a 1 and you plug in a 5. This time I didn't tell you, so we just have to try some numbers. So give me a number I can plug in. 0. Okay. If I plug in x equals 0, I get 0 minus 0 plus 0 minus 2. So we get a -2. Can you find a number that would give us a positive if we plugged it in? I put in a 1. Still negative. Let's try 2. So if I put in a 2, get 32 minus 24 plus 6 minus 2, and I get 12. Okay, last year all you would tell me was there's a sign change. So a 0 exists. Between 0 and 2, between those x values. But I need you to state something else, because it is only true if you have what kind of function. Must be true about our function for this to work. Continuous. Is this continuous? Yes. So I'm just going to write it's a polynomial, so always continuous. So when you do intermediate value theorem this year, you do have to state that your function is continuous. question. Would you mind handing those out? So assume f of 1 equals -5. So when x is 1, we get out -5. And f of 3 is +5. Does that mean there is a 0 between 1 and 3? Is that what the intermediate value theorem tells us? What else does the intermediate value theorem tell us? Has to be continuous. Did I tell you it was continuous? No. If it's not continuous, for all I know, I might have something like this. Is there a 0 in between those? No. So if it's not continuous, we don't know anything. So just be careful. We have to know it's continuous. That is the end of this section. So if you look, you were just given a handout for section 5, just the continuity handout. That is your homework. Tomorrow, of course, we have the homecoming stuff, so this will be due on Monday. Yes.
On my example 7, do we have to write the sign change between?
You should tell me, yeah, you should give me that conclusion there. Huh?
They're gonna have to learn to talk a lot more with you.
They don't like
And I can't hear, so they're gonna have to talk louder.
maybe getting, don't read the lips, that's what I'm doing.